Okay, so the first part of today's lecture is going to be about the squeeze theorem. And so what is the squeeze theorem? Okay, now if you have a function, this is our f of x, which is bounded by two other functions. Okay, so we have a g of x and we have an h of x. Now the squeeze theorem says that the limit as x tends towards a, now if the limit as x tends towards a of g of x equals the limit as x tends towards a of h of x, if both of these are going to the same spot, well, then the limit as x tends towards a of f of x will go to the same spot, okay? So it means if you have a function which is bounded by two other functions, well, the function in the middle has to go to the same spot as the other two functions if both of those go to the same spot. That's basically what it means. It means that if this function and this function is smaller than f of x, this one's bigger than f of x, if they're going to the same spot, f of x has to go to the same spot. In certain countries, in France, this is a rough translation, is two cops and a drunk guy theorem. So you have to imagine that these are the two cops, and you got a drunk guy in the middle. If they're both going to the jail cell, drunk guy is going to the jail cell. In Russian, it roughly translates to two militiamen and a drunk guy. And you'll see what I mean by the drunk guy, by how much, as much as it wibbles and wobbles around, if both of the bounding functions are going to the same spot, well, then the function in the middle has to go to the same spot too. So, let's first look at somebody who has a divergent property to it because it wobbles so much and because it moves around so much. So if I was going to investigate, let's say, the limit as x tends towards 0 from the right of sine of 1 divided by x. All right. So we can ask ourselves about this type of function right here. Okay, so as x tends towards 0, we could actually sample other points. Okay, so all right, x is tending towards 0, but we're talking about sine of 1 divided by x. And so when you're talking about sine of 1 divided by x, well, okay, so x is tending towards 0. So I can pick points like, well, x is 1 divided by pi, 1 divided by 2 pi, 1 divided by 3 pi, 1 divided by 4 pi, 1 divided by 6 pi, 1 divided by 1,000 pi. What happens with all of those 1 divided by pi's? They get flipped upside down, okay? So as x tends towards 0, what do we end up with? So we're tending towards 0 from the right. Now, the sine is always going to be bounded between 1 and negative 1. And sine is a wave. But as we, as we tend towards 0, the wave starts to oscillate in crazy patterns. I mean, not in crazy patterns, it just starts bouncing back and forth between negative 1 and 1 faster and faster, okay? So when we talk about divergence, or limit not existing, class last time we talked about, yeah, you can have something be a vertical asymptote and it can tend towards infinity, okay? Another case where a limit does not exist is what if this limit just ends up oscillating back and forth between 1 and negative 1 faster and faster and faster, okay? So this guy right here, this limit does not exist. Because as you approach 0, remember, you can't have a constant that's divided by 0. And so this inner limit right here, this actually tends towards infinity. And so since the limit of the interior tends towards infinity, how many times is it going to hit pi over 2, 3 pi over 2? Any of those. Pi over 2 times 1,000, pi over 2 times 1,000,000,000, pi over 2 times 1,000,000,000,000. But it's going to oscillate faster and faster and faster. Okay, so this is an example of a limit that does not exist because of its oscillations. How much it is wobbling between 1 and -1. Okay, so now we're going to investigate a slightly different problem. And this is going to use the property of the squeeze theorem. Okay, so instead of saying the limit as x tends towards 0, sine of 1 divided by x, let's say we were going to look at the limit as x tends towards 0 from the right of x sine of 1 divided by x. Okay. Now on this problem right here, sine of 1 divided by x is oscillating just back and forth between -1 and 1 repeatedly. Okay. But x is tending towards 0. So when using the squeeze theorem has a tendency to lend itself towards trigonometric functions. Okay. The reason for that is that trigonometric functions, well, sine and cosine, naturally have an inequality that works with them, okay? So if we look at the previous picture, what is the inequality that is going to, okay, so we need to start right here with an inequality and saying, okay, if I can create an inequality and say, okay, well, if both of the guys on the outside go to the same place, the guy in the middle goes to the same place, right? And so what is the inequality that we're going to be dealing with when talking about sine and cosine, okay? Well, the inequality that naturally arises is that, well, sine of x is a wave that's going to be bounded between -1 and 1. So that's where we're going to begin. So sine of 1 divided by x, despite the fact that it will oscillate, we know that this is true. Okay? We know that despite the fact that it's going to be oscillating, it's still going to be bounded between -1 and 1. Okay? And so then I could say, all right, well, this is not exactly what I want to investigate right here, but this is a natural inequality to begin with for this type of problem, okay? And so then I could say, well, all right, fine. It's bounded in that way, giving us a natural inequality. So why don't I just multiply everybody by x? Okay. So this would be, well, -x is going to be less than or equal to x sine of 1 divided by x, which is going to be less than or equal to x. Okay, so I'm just going to multiply everybody by x. All right. So now I have two functions that are actually bounding this inequality. I mean, bounding the function for the limit that I'm trying to deal with. And then I can say, okay, the limit as x tends towards 0 from the right of -x equals the limit as x tends towards 0 from the right of x. And if we just say these limits are tending towards 0, oh, well, they're just going to tend towards 0. Okay. And then and say therefore. So no, it might not be used to this symbol. Use therefore. The limit as x tends towards 0 from the right of x. Now sine of 1 divided by x equals 0. By the squeeze theorem. All right, so we begin with our natural inequality involving sine of 1 divided by x. And we just say, well, if I multiply everybody by x, and then say, well, both of those bounding functions go to 0, therefore the guy in the middle has to go to 0. But what is the graphical interpretation of this? Now, we have an x right here and a negative x right here, right? But the guy in the middle is oscillating like crazy. Okay, so we have our negative x and we have our normal x. And so So this is our x, this is our negative x, and then we're going to have our sine x, sine of 1 divided by x. So, now, this is what is meant by the squeeze theorem, or the two cops and a drunk guy theorem, is that as we tend towards 0, since I have a bounding function which is an x and a negative x, they're both tending towards the same spot. And so despite the fact that x sine of 1 divided by x wants to wobble and move around, both of those guys are headed towards the same spot, so that forces the guy in the middle to be squeezed into the same spot. And so that's why x sine of 1 divided by x will tend towards 0 in this case. Okay, so when I say two cops and drunk guy theorem, the drunk guy can wobble around as much as he wants, but x is a cop, negative x is a cop. They're both going to the same place, so they're both taking that guy to the jail cell. All right. Let's look at another one that also has to do with wobbling. But instead of wobbling infinitely fast, let's just say he just keeps on moving. So, let's say we wanted to investigate the limit as x tends towards infinity of just, well, instead of saying sine of 1 divided by x, let's just say sine of x. Right. Now, what does sine of x look like? Sine of x is a wave. It is a wave, it's going to stay being a wave. The limit as x tends towards infinity of sine of x does not exist due to the fact that, well, sine of x is a wave. It's always going to be bouncing back and forth between -1 and 1. So this limit, it never converges to a single number because no matter what, it's always just going to be a wave going, well, all right, I'm looking in the wrong direction. It's just going to be a wave. It's going to keep on being a wave forever. And so as it goes off to infinity, it's still a wave. And we say that the limit does not exist because it never approaches a single number. It's always just going to be bouncing back and forth in its normal during its normal periods. Okay. All right. So let's look at, since this is another example, something that just oscillates. It never converges to a single point. But at the same time, it is always bounded. Okay, so since this wave is always bounded between -1 and 1, it gives us a natural inequality. So if we look at a slightly different problem, maybe we can get it to converge to something. So let's say we said, let's look at the problem. The limit as x tends towards infinity. The sine of x divided by x. All right, now the function sine of x divided by x is actually a very special one, and we're going to examine this in multiple ways. When we get to some of the later exams and we'll talk about L'Hopital's rule, we'll talk about the limit as x tends towards 0 of that one, but we're not quite there yet. Okay. And one of the reasons that this is a very important function is that if you're doing modeling involving waves, it can actually serve as a source function. So, how would I start to investigate this problem? I want to use the squeeze theorem on this problem. Okay, so I'm going to begin with the natural inequality that occurs from the sine wave, as that the sine wave is always bounded between -1 and 1. And so, that's where I'm going to begin. Okay, so this is the place where I begin. The sine wave is always bounded between -1 and 1 because it's just a wave, okay? But I want to investigate this limit right here. So what I'm going to do is I'm going to begin with the natural inequality that occurs from the sine wave. And then I'm going to say, well, okay, but I want to investigate this limit. So why don't I divide everybody x by x? On the last problem, I multiplied by x because we were talking about x sine 1 divided by x. But on this problem, I'm going to say, well, -1 divided by x is going to be less than or equal to sine of x divided by x, which is going to be less than or equal to 1 divided by x. Okay. Now, I can say that the limit as x tends towards infinity of -1 divided by x equals the limit as x tends towards infinity of 1 divided by x. Both of those equal 0. So now therefore, the limit as x tends towards infinity of sine of x divided by x will equal 0. Okay. And now this is one of the reasons that the squeeze theorem has a tendency to lend itself towards trigonometric functions is because trigonometric, sine and cosine, they wobble a lot. But they begin with the natural inequality. So you begin with this inequality right here and say, okay, what I'm really investigating is this function right here. But I've got a place to start with, okay? And then you say, okay, if I start with this inequality, and then I divide everybody by x, and then I could say, well, all right, since I did that, well, the limit on the lower less than function and the greater than function, both of these end up going to 0. So the limit of the interior ends up going to 0. And so we can say, therefore, the limit as x tends towards infinity of the interior goes to 0 by the squeeze theorem. And now let's have a look at what the graphical interpretation of this would be. I don't want to use a new page, so I'll just borrow this one. That I kind of messed up before. All right. And so if I look at graphical interpretation of this, let's put that one right there. Call that -1. Okay, so this is 1 divided by x. This is -1 divided by x. And so if I draw my sine wave, yeah, my sine wave is still oscillating. But the oscillations are bounded by 1 over x and -1 over x. So as x tends towards infinity, what happens to the sine wave is that, the sine of x divided by x is that the sine wave actually just, it gets squeezed in tighter and tighter. So that's what's known as the squeeze theorem, is because we have two bounding functions that as they tend towards infinity, they're going to tend towards 0. And so the guy that's stuck in the middle, you can call 1 over x and -1 over x the cops. And then you have a drunk guy in the middle. He's going to wobble as much as you want. It doesn't matter. They're tending towards 0, so this guy has to tend towards 0 as well. Okay?